So we're going to talk about the detecting hardware Trojans in third parties IP. My name is Gustavo de Levante.
I'm David Choi.
I'm Connor Strombo.
And I'm Nicholas Broussard.
I'm Anik Roy.
So going into the background, what are hardware Trojans? They are malicious modifications of a device or integrated chip that are intentionally inserted during the design or manufacturing process. These modifications are intended to compromise the security or functionality of a device while remaining undetected. So why hardware Trojans matter with third-party IP? When the circuits are provided by third parties, there is not a golden reference to compare it to, since a hardware Trojan could have been inserted into the reference design. Third-party IPs can introduce security vulnerabilities embedded within the IP, allowing an attacker to manipulate the functionality of any chip using the IP. As circuits become more complex, it becomes infeasible for a hardware designer to create the design without the use of third-party IP. So it's all the more vital to be able to detect and remove hardware Trojans early in the design process. So there were four approaches for detecting hardware Trojans. The first is functional testing, which tests for suspicious circuit areas with varied input. The limitations is that it is non-exhaustive and requires manual oversight. The second is golden reference comparison, which compares against a known Trojan-free design, and the limitation is it is ineffective for third-party IP without a reference. The third is model checking, which verifies all states for Trojan absence, and the limitation for that is that it is unscalable for complex circuits due to state explosion. And the fourth is manual code review, which reviews HDL like Verilog for known or unknown issues. And the limitation for that is that it is time consuming and is prone to human error and is also not scalable. So the proposed solution is machine learning, which efficiently detects new and unknown Trojans and addresses the limitations of traditional methods.
So a method of detection that we use is detection with graph neural networks. So the process for this is the first step is the graph generation. So we extract an abstract syntax tree from the HDL design, and then a data flow graph is created to model the behavior of the circuit that we're analyzing. And then the graph is adjusted to remove redundant or unreachable nodes. And so then once this graph neural network is made, the application of it is it operates on the graph to detect where Trojans would be, and it approximates a theoretical detection function. So some advantages of using a GNN is that they're efficient for large circuits. So some circuits have millions of nodes and edges, so it would be completely inefficient to go by hand one by one to look at all these different nodes. And so GNNs are able to analyze really large circuits. There's an improvement in accuracy. It's able to identify subtle conditionally active Trojans and has low false positive rates. It has real-time detection. So some processes can take hours to days, but with a GNN, it can process the data in seconds. And for prefabrication analysis, it can detect the Trojans before it has gone to manufacturing, which saves cost.
And here's the methodology we used for project. So this slide outlines the methodology we used to evaluate the effectiveness of graph neural networks, or GNNs, in detecting hardware Trojans within third-party IPs. The focus is on identifying these malicious modifications before fabrication, which is critical for ensuring security and functionality. Our main objective is to leverage GNNs as a scalable and efficient solution to detect Trojans, especially in scenarios where traditional detection methods fall short. Methodology involves three key steps: extracting graph representations from hardware designs. These include the abstract syntax tree, which represents the code structure, and the data flow graph, which models signal relationships. Next is training a GNN model using the HW2VEC framework. This framework is specifically designed for hardware security tasks, making it a perfect fit for our project. And the third step is evaluating the trained model's ability to detect both known and unseen Trojan configuration. This step ensures that the model generalizes well and can handle real-world scenarios. The tools and technologies we use were first HW2VEC, which provided the framework for graph generation and model training, the TJ-RTL toy dataset, which is a curated dataset for training and validating the model, and finally PyTorch Geometric, a library that supports building and training GNNs efficiently. And in this slide, I'll walk you through the graph extraction process, which is a critical step in preparing hardware designs for analysis. So we utilize the HW2 graph pipeline for generating graphs from hardware designs. This pipeline allows us to convert raw Verilog HDL code into a structured graph representation that can be processed by our model. The first step in the pipeline is pre-processing. Here, individual hardware module files are combined into a single flattened file. This process eliminates duplicates and simplifies the graph structure, reducing its overall complexity. Next is the graph generation phase, which involves three key substeps. PyVerilog is used to extract the abstract syntax tree from the Verilog code, and then the AST captures the syntactic structure of the hardware design. Then the AST is converted into a data flow graph, and these DFG models model the relationship and signal dependencies within the circuit, providing a deeper understanding of its functionality. And then finally, all individual signal DFGs are merged into a single comprehensive circuit graph that represents the entire hardware design. And after the graph is generated, wait, can you go back? It goes through a post-processing stage. Here, redundancies and disconnected subgraphs are trimmed. The resulting graph is outputted in a JSON format and then converted to a scalable network-X graph object for efficient analysis. The final result is a complete graph representation of the circuit, and this representation is now ready for analysis by our model, which will enable us to detect potential hardware Trojans effectively. This slide covers the model architecture and the training process we follow to detect hardware Trojans. And so first, the model we use is a GNN-based architecture optimized specifically for single graph classification tasks. It's designed to process the graphical representation of hardware circuits and predict whether they're Trojan-free or Trojan-infected. And let's break down the layers of this model. First, we have the input layer. This layer takes in node feature vectors, which represent the signals in the circuit. Each node carries important information about its role in connections. Then we have the graph convolution layers. These layers aggregate information from neighboring nodes to capture both local and global relationships within the circuit. This allows the model to understand the intricate dependencies in the graph. And then we have the attention-based pooling layer. This layer identifies the most critical nodes in the graph by analyzing their activity levels. It helps focus the model's attention on the most relevant parts of the circuit. And then last is the output layer. This final layer predicts the probability for two states where the circuit is Trojan-free or Trojan-infected. For training, we followed a structured process. The dataset was split into training and validation subsets to evaluate the model's performance. We employed single graph classification tasks, as the objective is to classify each circuit, whether Trojan-free or Trojan-infected, and hyperparameters like learning rate, dropout rate, and number of training epochs, which were just a couple of the hyperparameters, were tuned to achieve optimal results. And that's it for model and training.
So to evaluate the success of the GNN model, we're going to use benchmarks for comparison. So the model will be compared with existing solutions that are available on TrustHub for detecting hardware Trojans. And so the evaluation criteria, there's three important measurements. The first is precision, which is a measure of the true positive rate of detection compared to the true positive and false positive rate. There's recall, which is a measure of the true positive rate compared to the true positive and false negative rate. And there's the F1 score, which accounts for both precision and recall, and measures both of those results to provide informative analysis of the efficacy. The trained model will be compared to the reported results from the GNN42J to determine the viability of this method for the detection of hardware Trojans.
All right, and then we have the demonstration of the process. So for this, it's going to be a video. We don't need to watch the whole thing, but it's an overview of what you need to do to get this project up and running. So the first thing you can see here is we start in the directory. We have a Conda installation, and so we're going to be using this environment YAML file in order to initialize Conda. So if you look through here, it's just got all the dependencies required and has the versions pinned so that you can tell that this version will work as long as you use these specific dependencies. And then next up, we have the randomized testing script that we use to test a bunch of different random hardware or random hyperparameter values. So all this really does is takes a YAML file, randomizes the hyperparameters within a set range, outputs it, and then runs the use case 2 Python script, which will train the model and then evaluate it on the toy training data set. So I go ahead and activate the environment here, or create the environment first that is already created, so this is going to fail. And then I go ahead and activate the lab environment. And then once that's done, we can go ahead and run the randomized testing script. We're going to have that reference the use case 2 Python script and the toy training, the toy data set, sorry. And then when we go ahead and run that, we can see that it's randomized the values here. Learning rate has been set to the same as the default value. Seed is, of course, different. It doesn't particularly matter, but we did find surprising correlation with the initial random seed and the quality of the output. And then we have a couple different things here. The first number for each of these is going to be the one that was chosen. The second number after the hash is the default value. Everything here was chosen to be fairly close to the default value with some variation. A few of these things are going to be set to the same as the default value anyways, just to simplify the process. And then this will take a while to get the first part of it started, so we can go ahead and skip through a little bit. Maybe skip forward by about a minute or so.
You can see trial 2.
Could you skip forward about a minute?
I think I did. On my side, you can
Okay.
see trial 2. I don't know if you can see it on your side.
Okay, I see them. I can't see it on my side, but so we have each trial run. They run for a variable length of time. Some of them only take a couple seconds. Some of them can take a couple minutes to hours. but you can see the output of each of the trials. And once that's done, it all gets collated into results.txt, which is just going to be the best results from each of the trials. And then using that, we can move on to the comparison of the hyperparameters that we evaluated. So this list has the list of everything we randomized, and these were chosen kept within the same order of magnitude as the original values for each of them, with some more variation for the hidden units and the training epochs. That was just done to make the process more straightforward for the most part. I didn't want to choose anything that's unreasonable. And so because of that, we can then move on to the results we have.
Can you see on your side, Nicholas?
No, it looks like I'm way behind. Okay, I can see you in the slides though, so I'll reference that. Okay, so the results we have here is the initial learning rate had a fairly high correlation with around the 0.005 being a good reference value. Number of epochs had a bit of variation. It looks like 1 to 200 seems to be better, but there is a spot around 350 that also did fairly well. The random seed surprisingly did have some correlation with seeds between 10,000 and 20,000 having a much better F1 score. Which is a little counterintuitive since it would be assumed that the random seed would have effectively no effect. And then we have the number of hidden units. It seemed largely uncorrelated, but better, or a larger number of hidden units did seem to perform well. And then moving on to the next slide, we have the dropout rate seemed to perform well around a key probability of 0.4, which puts it at a dropout rate of 0.6. Layers in the neural network performed well at 4 and 5. The number of groups in the batch is the number of graphs in the batch is the number of graphs that were tested at once. This performed surprisingly better at 1 and 2. I don't know why it had an effect, because I would have assumed that this should be uniformly distributed. And then we have the interval between many evaluations, also largely uncorrelated. And then moving on to the last parameters, we have the dataset splitting ratio, which is how much of the dataset was used for evaluation versus training. Obviously, when most of the set is used for training and then the rest used for evaluation, there are better results. And so we can see that with a data splitting ratio of 0.1, it performs best. And then as it goes to 0.9, there's a lot more bloom on the outputs. And then ratio for graph pooling seems to perform roughly well most of the time. Looks like 0.7 performed pretty well. And then we can move on to the final results of the top 10 performing. And we can see that a couple of the options here have some correlation, seem to have very similar weights for everything. So this is all just going to be a log scale so that everything can be displayed at once. But so it looks like the second, third, and then the 7th through 10th place all appear to be fairly similar, indicating that those are likely fairly close to the optimal values for running the model. And then from there, we can move to the comparison.
All right, and so here we can see the results with the optimized GNN. We can see that we got a precision of 100, a regular of 100, and F1 of 100, so we get the right results every time. Of course, an improvement of the baseline of an 87.50, a regular of 100, and an F1 score of 93%. And there's a conclusion to this project. We can see that the GNN is a great way of detecting third-party IPs, Trojans, and it achieves a perfect metric of the precision recall on F1 of 100. And also it shows that scalability of the GNN, I said previously, that it's being able to do GNNs with hundreds of thousands, millions of edges and nodes. So it's a very good, very advantageous, very cost effective. It can be put early on the in the process of making this, so you can save a lot of money. And again, the scalability is amazing for this. And with the validation of this data testing, we can see that it is good on validation sets, not only on the training one, of course. So it's good for on-scene data, and it's great for detecting the IP, the Trojans IP. Thank you.